Hello there, I'm Robert Nawrath, your guide into the world of functional safety. As the functional safety manager and functional safety engineer at Digital Core Design, I'm here to share some insights on the functional safety in CAN IP cores. FUSA is a wide topic and it is not only limited to automotive industry. I assume that functional safety is not everyone's cup of tea yet, but I've got a master plan to help you get into the topic. First of all, I will introduce our company. After that, I will discuss why safety is so important and how do we achieve proper safety level in our products. And finally, I will provide a brief summary. Picture this. Digital Core Design was born in 1999 in the heart of Poland, and next year we are celebrating our 25th anniversary. It's a quarter century of innovation now. Our design hub resides in the European Union, but our cell offices span the globe. We focus on three main areas. First, crafting intellectual property core and system-on-chip development. Second, we breathe new life into the end-of-life components. And third, we are pioneering innovative projects think cryptography and beyond. Our solutions are the breathing hearts of electronic devices worldwide, and we have countless satisfied customers. Now, let us take a glance at the crème de la crème of DCD's IP cores. All were born from pure innovation. Have you ever heard of the world's fastest 8051 CPU? Our implementation is 75 times faster than the original Intel version. Next up, meet D32 Pro, a fully scalable and royalty-free 32-bit CPU. And finally, but the most important one for us today, the CAN-all IP core, a full CAN ecosystem. I'm about to focus on this IP as a good FUSA example. And now our safety journey begins. Have you ever doubted whether safety is a must-have? I'm here to unreveal why safety is the key to unlocking success. Oh, sorry. Our company, DCD, is not the only one that takes safety seriously. Here we have a few examples from the latest electronic trade shows. Everyone says functional safety is crucial, and everyone tries to somehow implement these requirements. As far as automotive industry is concerned, the ISO 26262 is essential. I can say it's the functional safety Bible. The automotive industry has adopted stringent process throughout the supply chain. To get the final product approval, in example for a car, every single step must be traceable. You need to provide all the necessary work products and safety analysis. From the IP design house point of view, the safety analysis can be spread between IP provider and IP integrator. A product without safety documentation is cheaper, but the final time to market is long due to the time needed for the safety analysis. A product which is said ISO ready provides all the safety documents and analysis prepared for an assumed scope and operation environment. One could consider this ready component or a certified one more convenient due to the more time-consuming work done by the IP provider. And this allows also to save money because only the final product is certified and all the subcomponents are not obliged to be certified. I have already repeated the word safety many times, but what does it exactly mean? The automotive industry develops really fast. And since the time of Ford T, when the car was a fully mechanical experience, a lot has happened. After many people died, the lessons have been learned and safety mechanisms have been added. Also, mechanisms making our life easier have been added. Just to mention some of them: seat belts, automatic braking, power steering, airbags, electric window steering, and so on. Nowadays, cars are becoming autonomous and they do not require any driver presence, supervision, and we have to say that each additional safety-related and not safety-related element does extend the final product complexity. The more complex the design, the more failures may occur. And even the best engineer is not capable of taking care of every single design detail. You can say you have debugged your software and it is assumed faultless. You can say you have nearly 100% cut coverage. You do everything using the best design procedures and practices. And what? Still, an accident may occur. Why? Due to the wrong design assumption. The engineer cannot rely on the design itself, but the design must consider the real working environment and it must consider the random faults. This is where functional safety makes us change the way we do. We need to rethink the whole design. It is not only about what and how do we implement in our IP core. We need to think what can go wrong and how can we deal with it. Safety is all about to minimize the risk by addressing possible hazards caused by the malfunctioning behavior of electronic and electrical systems in a vehicle. A hazard is the dangerous situation and possible source of harm. If the possible failure modes and safety mechanisms are taken to design assumptions, the device handles the hazards in a known way or bring the device to a safe state which does not endanger the driver. I could also say, according to what Rainer said, we have a checksum in CAN bus. Okay, but what if the checksum counting unit fails? We need to be prepared for such a situation. The before mentioned ISO 26262 indicates the whole design lifecycle, from the item definition up to its decommissioning. You can see the so-called V lifecycle model. It is not only for hardware part, but for software part as well. To gather an objective evaluation of the functional safety of a product, the automotive safety integrity level has been introduced. In one sentence, it shows if the design provides a reasonably low level of failures in time. This one depends on systematic failures and random hardware failures. The systematic failures can be omitted by a change in the design, proper design procedures, and testing. But random hardware failures cannot be omitted. But the risk caused by a hazard can be mitigated. To achieve proper functional safety level, the design must meet international standards. Our DCAN IP has been designed in accordance with ISO 11898 and tested against ISO 16845 protocol conformance test specification. All this combined with our internal test is obligatory. When ISO 26262 knocks, every IP feature answers. with a detailed test report, no less. All this shows the design maturity, which results in final customer satisfaction. Now, let's us dive into the heart of it all. The DCAN as an ISO 26262 safety element out of context. The CIOC, in case of the DCAN, the soft IP CIOC, is an element developed and analyzed in an assumed context of use. Example, target FPGA board, memories used, etc. The CIOC is delivered with complete ISO-required documentation. Why? To help the system integrator, who must re-evaluate the safety analysis based on the target system and the safety analysis of other system components. The CIOC provides deep knowledge about the DCAN IP, its failure modes, safety mechanisms that enable to reach the required ASIL level, complete failure mode effects and detection analysis, as well as a step-by-step instruction to help to integrate the IP into the customer system and to conduct the system-level safety analysis. After third-party independent audit, the DCAN has reached a single point fault metric above 90% and latent fault metric above 60%. So it is ready to be used in automotive safety systems at the level ASIL B, but we are optionally prepared to deliver higher ASIL level IPs. Safety is crucial. The CAN bus controller is only the tip of the iceberg. Depending on the implementation environment, the IP integrator has to choose the IP that best meets his requirements. In example, the implementer can choose between Lean or CAN bus depending on the bus throughput or the safety requirements. If you think of safety since the project began, you spend funds. You avoid product recall, you get ready for product approval and certification, and get a lot of work done by someone who best knows his IP or device. Now get ready to dive deep into this safety analysis. The main work product is the failure mode effects and detection analysis, but it will be described later on. As the input product to the FMEDA analysis, we need to do a hazard analysis and risk assessment. We need to define the safety goal of our design and then ask what can go wrong and what can we do to react for this situation in the safe failure time interval so that it won't harm our driver. We need to detect the most failure modes that can lead to safety goal violation. To do so, one should estimate these three factors shown in the table on the right side. Exposure. How likely is the case to happen? How possible is the system to fail? Next, controllability. What is our ability to control the failure? Is the driver able to handle it? And finally, severity. How harmful can be the occurrence of the hazard? What harm can be caused to the driver? Depending on severity, we need to choose what is the target ASIL level that we need to reach. Knowing what can endanger our safety goal, we need to formulate the functional safety requirements needed to avoid any unreasonable risk for each of the hazardous events. Based on these functional safety requirements, we need to formulate then the technical safety requirements that indicate the safety mechanisms needed for detection of the detected failure modes. And now it's time to introduce today's star, the FMEDA analysis, which gathers all the information together. FMEDA, as you can see, is done in the form of a table. There are plenty of dedicated software solutions that should help us in conducting such an analysis. But all of them have one common disadvantage: price, which is not only relatively too high. Is the before mentioned software the only way? Thanks God, not. As a simple Excel sheet is good enough for the analysis. Each failure mode in our FMEDA must have a unique ID assigned to it and a description of the detected failure mode and possible effect on the analyzed item. In next columns, we need to estimate the distribution of permanent and transient failure rates to calculate their failure rates measured in failure in time. This is the failure rate for the particular failure mode in the absence of any safety mechanism. Then we need to assign whether this failure mode leads to a single point fault or multiple point fault. The multiple point fault requires at least two mechanisms to fail simultaneously. After that, we think of the safety mechanism that can detect the fault and estimate the diagnostic coverage. So we need to define how likely are we to detect this failure mode. The failure rate of a safety-related hardware element, in example, our CIOC, consists of the safe fault failure rate, these are the failures that don't endanger our safety goal. A single point faults failure rate, multiple points failure rate, and the residual failure rate. Based on these coefficients, we need to calculate the functional safety metrics. The single point fault metric, which depends mostly on single point faults, which most endanger our safety goal, and latent fault metric, which depends mostly on the latent faults. These are these faults that are hidden for our safety mechanisms, and we cannot react on them. Based on these values, as we can see in the tables above these coefficients, we can see that for an A0B component, we need single point fault metric above 90% and latent fault metric above 60%. These are these values that our CAN IP has reached. And hold up, folks, I can't spill secrets. We have to break a little bit because at this moment I can't share more information about the details of the safety analysis, the safety mechanisms introduced to our design, and metrics calculation, because it's our know-how. If you are hungry for more, please reach out to us. We are here to help you. And last but not least, why it's worth to integrate a CIOC into your design instead of to conduct the safety analysis on your own. Here are some tips, but I think of 4 words that you should remember: quality, cost, support, and time. As I already have said, the functional safety does cover software too. And we need to say that modularity is a must in newer projects. Every project is done from different elements in different abstraction layers. If an engineer replaces a deprecated element with a newer one, instead of building a new design from scratch, he wants to update the design that is already prepared. For example, you can change a deprecated CAN controller to a CAN flexible data rate controller just to gain the new features. As the physical layer is concerned, it is backward compatible. But what if the design has a ready application layer? The DCAN driver enables access to the device and can be easily integrated with an existing CAN stack. Example, CAN Open or even AutoSAP. This stack might also be used with an already existing application. So combining all the standard elements with standard interfaces, the replacement of one block with another one offering the same functionality, but for example, newer or faster one, should be as simple as changing a Tetris block with another one with the same shape, but different color. A good modularity example is the Socket CAN API. It's the official Linux CAN API. Each Linux application is developed independently from the underlying hardware. The Linux operating system offers a set of mechanisms to connect a user-space application with a kernel module. The kernel module, also called the Linux driver, is responsible for the hardware management, configuration, and data transmission reception. For example, if the application needs to use CAN0 device, the operating system invokes this device and every access is forwarded to it. Socket CAN is the driver networking layer created by Volkswagen Research. It's an open source project and takes the most opportunities from the network device. It's not as limited as the previous character device implementation. It uses the Berkeley Socket API, so the use of a device is as easy as opening a network socket and writing or reading from it. The abstraction level is maintained, and the device driver benefits from the existing queuing functionality. The Socket CAN API is very similar to a typical TCP/IP layer model. This similarity to network programming is the key to programming success, because the programmer does not need to learn how to use a CAN device, how does the physical layer work. He only focus on the application layer. It's a pure software work. And just to mention that the available on-market CAN FD stacks are built upon an existing CAN driver, and they are operating system independent. So the Socket CAN can be easily integrated into them. And so we have this modularity. It can be easily added to another system that already exists. For us as a proud member of the CAN in Automation Association, safety is not just a buzzword. It's our new way we do. I'm convinced that we all take care of delivering the best products to market. And I'm sure that safety is the best way for us all. Just to sum up, safety is not a slogan, it's a must. Our IPs have already reached the intended ASIL level. As for us as an IP provider, the introduction of the safety design flow has many advantages. It improved our existing IPs, our procedures, and so on. The IPs are already prepared also for another industries where automotive is the most important one. The ASIL-ready IPs have boosted us to the automotive industry because not everyone likes to do the safety analysis on his own. Thank you for joining me today. Remember, your safety is our priority. Stay curious, stay safe, and don't hesitate to enter the world of functional safety. Thank you.
So thank you very much, Mr. Nawrath, for your interesting talk. So you said you can use it in parallel to an existing stack like can open. So what does this mean when we think about can open safety? So there exists already a safety protocol. Do they complement each other? Are they somehow contradicting, or can you say something with regard to that?
If the CAN stack is already certified, then these two elements complement, because if you have one part certified, you need also this underlying hardware to be functional safety certified. So if you combine a certified stack with a certified hardware, you need to do this safety analysis on the system level. And all these blocks are already prepared for you. You don't need to take care of analyzing these elements on their own. You have ready analysis and you just combine them both together.
Okay, got it. Thank you very much.